So the microscopic quantum degrees of freedom black hole are encoded by the two-dimensional surface, by the horizon. And then more recently, type of systems where this kind of holographic behavior is encountered is entanglement entropy, which also quite often behaves. It scales with the size of the boundary of the systems rather than the volume. So the basic motivation behind the AdS CFT correspondence is the correspondence of the symmetries in the case of CFT, and this is why it is important to have anti-de Sitter space. So the group of isometries of anti-de Sitter space in d+1 dimensions is SO2, D, which is the d-dimensional conformal group. So if we study representations of this group in d-dimensional space, these are operators in CFT, and in AdS d+1, these are fields, in general gravity fields. So if we have on CFT side, what we can have minimally is the stress energy tensor, which is spin 2 operator. On the dual side, we have a spin 2 tensor, which is the matrix as a minimum setup for a theory. Okay, before continuing about AdS CFT, let me now shift gears a bit and talk about Chern-Simons theories and relation to boundary degrees of freedom. So Chern-Simons theory, the Lagrangian of Chern-Simons theory produces trivial equations of motion. So you have the field tensor or curvature tensor for the connection A is equal to 0, which in the first approximation says that the theory is trivial. Then only all of the connections are just pure gauge. Well, you can still, Hamiltonian of this theory is 0. So the partition functions are just numbers. You have to calculate the trace of the unity operator of some appropriate Hilbert space. So there's some numbers. They're interesting numbers, but nevertheless numbers. Well, what you can do, you can allow some singular gauge transformations. So what these singular gauge transformations do, they still locally preserve 0 curvature condition, but they introduce delta function singularities. So introduce sources. In this case, you can represent the space. For example, in this case, this cylinder represents a three-dimensional space, which is split into time direction and transverse Riemann surface. So these delta function singularities, they are these lines which can be thought of trajectories of particles in this space. And in this case, the partition function is just you have to compute the trace of the Hilbert space, but not of the unity operator, because you can also permute these particles. So the particles can braid, as shown in this picture. So when you compute the partition function, you have to close this cylinder and compute the trace of this operator, which can be thought of diffeomorphism that in fact just acts on the boundaries of this cylinder. So a bit about this Hilbert space that appears in the trace. Well, it was discovered that from canonical quantization of Chern-Simons that this space is the space of conformal blocks. In particular, if you take, for example, a partition function of Chern-Simons on a space with a boundary and compute the function and integral, what you'll get is a wave function which is in some way a conformal block, or more precisely, the wave function can be expanded in the basis of conformal blocks. So in this case, you have a space with a bound. This is the boundary. There are some sources or Wilson lines inserted, and because the theory is topological, so the curvature is 0, you can change the positions of these curves, and you can actually draw them on the boundary of the space. And this particular state of Chern-Simons can be mapped into a vacuum conformal block. Or if you braid the points on the boundary, if you interchange the positions of the points, you just change a state in this Hilbert space or where conformal blocks form a basis. If we're talking about SUN theory, SUN Chern-Simons, this is the conformal blocks of SU-minimal models. But there will be some generalization later. So this picture in particular prompted people in the beginning of 90s to, as one of the applications, to call this, to associate the states of the quantum Hall effect with conformal blocks. Because if you assume that quantum Hall effect is described by Chern-Simons theory, then you can think of this correspondence between states of Chern-Simons and the states of conformal block. And then I think in this original picture, you could think of this insertions at these points as the quasi-particle excitations of the quantum Hall state. So I'm not going to talk much more about it, but I just referred to the talk by Paul Wigman last week, who talked about, in particular, the Laughlin wave function in the quantum Hall effect. Coming back to the states, so I can take a scalar product of two states, and then I get a closed manifold with no boundaries with the closed Wilson loops inside. So this is this kind of partition function or functional integral computes a topological invariant, an expectation value of a Wilson loop operator. And these quantities are non-trivial observables of Chern-Simons theories. So they are characterized by the manifold. They are characterized by a group, by the representations of the Wilson lines, and also by the coupling constant of Chern-Simons. So the group and the coupling constant, they are mapped to two quantities, in this case denoted A and Q. This is more, I guess, mathematical notations for the combinations of the rank of the gauge group and Chern-Simons coupling constant. So just a small digression to relate to things that discussed at this conference. So this expectation, these topological invariants of knots, they are the basic observables of Chern-Simons theory. So they take values in some. So they are generally they are rational functions of or polynomials of several parameters like A and Q in this case. So the theory of knots and invariance of knots is closely connected to representation theory of the braid group. In particular, if we take this relation that I've shown before, if you can think of this diffeomorphism K that acts on the boundary of the cylinder as a braid group operation that interchanges or twists the lines. And then computation of the partition functions or Chern-Simons theory expectation value is equivalent to constructing some representation of braid group and computing the trace in this representation. And this K becomes some, let's say, an element of the braid group, which intrinsically has, well, by definition, the braid group has satisfies Yang-Baxter equation, and this just follows from a simple picture here. And that was used later in the 90s. That was used as a method to compute knot invariance. In particular, if we have an R matrix that satisfies Yang-Baxter equation, you can use this R matrix as representation of a braid group and compute knot invariance. that was more physical way of computing that, but alternatively, mathematicians used more algebraic methods. In particular, one method is connected to representation theory of Hecke algebra, which is an extension, or this is an algebra of a finite dimensional algebra of infinite braid group, because apart from the Young-Baxter relation, it has an extra quadratic relation on the generators. And you can think of this quadratic relation as a deformation of the, well, this Hecke algebra is a deformation of the permutation algebra. So when Q is equals to 1, you get just the permutation group. So representations of the Hecke algebra can be constructed, derived, or in some way starting from representations of the permutation group. And one example, more recent example that I would like to mention is the double affine Hecke algebra. So this is an extension of Hecke algebra that introduces spectral parameters. In particular, so the first relation in this algebra, so there is a number of generators. It is based on the fact that braid group is equivalent to while group of certain of simple E algebras. So you can consider affine Hecke algebras. They correspond to affine while groups. So you can elaborate this construction a bit more. So that was done by Chern-Simons in the 90s to construct this extension that also incorporates the spectral parameters in the algebra. So it looks a bit complicated, but it's a nice algebra, which in particular helped Chern-Simons to prove some relations about for symmetric polynomials. But later, he also came with a proposal how to compute knot invariance using this algebra. I'm not going to explain this much in details, but it is based on the usage of Macdonald's polynomials, which make the space of representations for this double affine Hecke algebras, and you can, in a way, in a simple way, you can think of them as this wave functions of the Chern-Simons theory. So basically, the construction works like this. You start with Hecke polynomials, with Macdonald polynomials, and you act with the well, in fact, with automorphism of this Hecke algebra to produce a knot that would act like a braiding operation to produce a knot, and then from that you can extract the invariance, in particular Jones polynomials, but you can also have more general polynomials. And this works well for a particular class of knots, which is called torus knots. They're especially nice. You can get general results for, so torus knots, these are the knots that you can draw on the surface of a torus without self-intersection. And in this case, you can derive some very nice general formula for these knots without using R matrix. So you don't need to know R matrix. In particular, you can use this Hecke algebra, double affine Hecke algebra, or Chern-Simons algebra to derive general results relation for any torus knot. And a few years ago, we tried to extend this construction to other knots, but other knots, well, for other knots, it is not possible to avoid this step of calculating R matrices, representations of R matrices, and probably in this way, to do this really, so at the time we didn't succeed, probably this procedure that was explained last week by Paul Zinjosten can help in this case. I'm not sure. Okay, so I'm coming back to AdS CFT, and to a low dimensional case, to three-dimensional gravity. So this is the action for gravity in 3 dimensions. There's a cosmological constant. So I can think of this AdS space as the interior of a cylinder. The simplest solution is the anti-de Sitter solution, but in 3-dimensional gravity, it is also like a Chern-Simons theory. It is almost trivial, so you can relate any 2 solutions by a gauge transformation, so all solutions, they are locally equivalent to AdS anti-de Sitter metric. So in this case, the isometry group of anti-de Sitter space is SO2,2, but as we know in conformal theories, if we want to compare this to conformal theory, in 2-dimensional conformal theory, the conformal group is infinite. So where does this come from? Well, in this case, here it is. So in '86, Brown and Ono discovered that if you put some boundary conditions on the solutions, if you put so-called Brown and Ono boundary conditions on the metric, and you study which kind of diffeomorphisms preserve this metric. So there are trivial diffeomorphisms that do not change physical charges, but you can also have non-trivial ones that will produce physically different solutions. And these solutions are black holes. So what you can find that the associated charges, they commute they close to form Virasoro algebra. And this is the extension of the naive SO2, SO2 conformal group. This is provided that you associated the central charge of this algebra with this relation, the ratio of the L parameter that defines the size of the cosmological constant over 2G, where G is a Newton constant. So usually in AdS CFT correspondence, you have to require that, well, you want to work in the regime where gravity is weak. So this G, so it is well defined when G is small, when gravity is weak, which means that the central charge should be large. So this correspondence between AdS and CFT should work in the limit of, should work well in the limit of large central charge if we want to incorporate classical gravity. So here's a coordinate transformation that changes the solution. So starting from AdS solution, I produced another solution which is now has a horizon when m is a positive number. So for this particular solution, for positive m is a black hole. For m negative 1, it gives just empty anti-de Sitter space metric. And for generic negative m, it is a metric with a conical defect. So it can be a conical deficit or conical profficit. So this is the deficit angle for negative m. Well, it was noticed also then in the 80s that 3D gravity can be mapped to Chern-Simons theory. So if you consider an SL2R cross SL2R Chern-Simons theory, so there is a pair of left and right gauge fields, and I want to change a basis basically to write it instead of SL2R cross SL2R as explicitly as a SO2, 2 theory. I just change a basis, introduce 2 fields omega and E, and I consider the Chern-Simons action where I just take the difference of left and right Chern-Simons actions. Then what I get is up to surface term, it is just an Einstein-Hilbert action in the first order formalism. So for if I identify E and omega with the Vielbein and the spin connection respectively. And this is the connection between coupling constant of Chern-Simons and the gravity parameters. So K must be C over 6 in this correspondence. Well, it is a complicated question from the point of view of people studying gravity theory is how to couple higher spin fields to just regular gravity. And in this Chern-Simons picture, it comes automatically. Instead of SL2 cross SL2, you consider SLN cross SLN, and this gives you higher spins consistently coupled to the metric. So how you can get gravity solutions from this? So you need to consider special gauge transformation of flat connection, of constant flat connections. So you can start with a constant flat connection in just SL2 case. Let's write it in terms of generators of SL2 algebra with some parameter m. And then I do a gauge transformation on this constant connection, some special gauge transformation also involved in some an SL2 generator. So if I use this connection between A's and omega and E, I get exactly the same metric that I've shown before. So that's a black hole, a flat connection that corresponds to a black hole. Yeah. Right. It is not flat. I mean, it is not flat gravity background in this case. It is flat connection in Chern-Simons. It corresponds. Take a flat connection, but it's a Chern-Simons flat connection. It is a connection in Chern-Simons, so it's a Chern-Simons field. It's a gauge connection, but you can map it into a gravity solution. You can map it in 3 dimensions. If you write gravity in first order formalism using field binds and spin connection, they are just SL2R fields. So you can. Well, well, you can actually have different geometries. For this specific choice of boundary conditions, you get anti-de Sitter geometry. But you can also have asymptotically flat geometry that would be based on a slightly different group for the Chern-Simons. So instead of SO2,2, you would have probably PSO2,2 or something like that. But the geometry here is anti-de Sitter space, 3-dimensional anti-de Sitter space. Right. In general, you'll produce slightly different metric, but because in 3-dimensional case, again, the gravity is trivial. So the only difference is if you use some kind of singular gauge transformations that you can change. Well, in what you can, the only thing you can do in Chern-Simons, you can introduce Wilson lines by these gauge transformations. So equivalently in gravity, you would introduce. In geometry, you would introduce black holes. So you'll have also some kind of Wilson lines there. But locally, again, the space is anti-de Sitter, but you'll have things like horizons, for example. And well, there will be singularities, exactly. So there'll be like black holes. So this gauge transformation is singular, so it introduces singularities. That's, I guess, in some way was my next slide. And yes, so this, as in Chern-Simons, gauge transformation introduced Wilson lines. Here introduce black holes that, or more generally, you introduce a particle, a massive particle that is coupled to the metric. And now the massive particle is the source of gravity field. Now, this massive particle, you can think of it as having mass and a spin, and this mass and a spin, they will be mapped into the representations of SL2 cross SL2. So just in this case, you should always assume that the mass is, or in terms of dual CFT, the conformal dimensions of the operators, they are large. So you should always consider the limit of large central charge. So the black holes, they correspond to, from the CFT point of view, they are heavy operators. Let me come back to this in a moment. So you can go further, and that this is a topic of recent works. You can, although the correspondence between Chern-Simons and gravity was known since the 80s, but the more recent observation was that you can also study the observables in these theories. And in case of Chern-Simons, you can study Wilson loops, which correspond to knots, but you can also study open Wilson lines. So they are, in a simple explanation, they are just they're some kind of conformal blocks. So this is what you can also study. And on the gravity side, what you can study is, well, how particle, if you have a particle that couples to gravity, then what you can measure, you can measure the action of this particle, or the geodesic length of the world line of the particle. So if you do a simple calculation in de Sitter space, you'll find that for a specific Wilson line, so this Wilson line this is some kind of composite Wilson line. You have SL2 cross SL2, so you have two gauge fields. You compute P exponential of one connection over contour C, and another one in the opposite direction, or C bar. There's the same contour, but in the opposite direction. So again, you have you need to take a trace and some representation. That would, in the case of gravity, you should compute the action with the massive. You should compute massive particle action. So if you just do this calculation, you will find that the Wilson line is exactly equal to the, well, exponentiated length of the geodesics between 2 points x and y in the bulk. And the mass in this case would correspond to mass squared is the quadratic Casimir of the representation. And you can compute if you put the endpoints of the particle of the Wilson line close to the boundary, so at the endpoint at the surface of the cylinder as shown here, then you can find that the length of the geodesic scales like this, and this is one of the manifestation of the so-called holographic formula for entanglement entropy, which says that the entanglement entropy, the conjecture is that the entanglement entropy is the length of the, in general, it's the area of the minimal surface, but in 3 dimensions, just the length of the geodesics divided by 4G. So using the identification between G and C, you get this known formula for entanglement entropy. More generally, what you can compute beyond that, you can compute correlation functions. So in this case, what you can compute using classical gravity is the C going to infinity limit of correlation functions, for example, 4-point correlation functions, where the two operators, well, all the operators, they have their dimension, their conformal dimensions are large, and they scale as C, but the one pair of operators is even much heavier than the other one, so which corresponds to computing the 2-point correlation function in the background created by these heavy operators. And so these heavy operators, they create a background which in terms of gravity is just a black hole solution. And in this background of this black hole solution, you can compute a Wilson line, or you can compute a geodesic distance in this background, and that will compute a 2-point correlation function. And you can compare this with the calculation in CFT. So this limit is also accessible in CFT. It is called semi-classical limit. And in this limit, this correlation function is dominated by WN vacuum conformal block. So entanglement entropy in this picture just corresponds to a specific choice of a representation of this light Wilson line. So you can elaborate. You can come up with some explicit formula to do the computations. So let me just comment on how you do this in SLN case. So just a reminder, in SLN you can split the generators of the group in representations of principally embedded SL2. So you can split all the generators in groups of labeled by spin from 2 to n, and with each group will have a number of generators which goes from -s-1 to s-1. Then all these generators will, so the generators with any s will be in the representation in S representation, spin S representations of SL2 of the same group. So if you want to compute the correlation function, so what you need to do, well, in terms of this picture, you need to specify the background. So you have to choose a flat connection that would describe you the situation of the black hole. And then you have to fix a representation that will tell you which kind of Wilson loop you want to compute. Then you can reduce this problem of computing these p exponentials into a problem of calculating the trace of some metric. So you can trade the algebra fields into group fields, and then just so the Wilson line will be just a trace of the product of the operators of the group elements at the endpoints. So there is some matrix Q. You would like to know the eigenvalues of that matrix. If for these particular backgrounds that correspond to anti-de Sitter solutions, so you start with some constant flat connections. You do a special gauge transformations. In general, in SLN case, the formula for flat connection, small connection A, you just take L1 SL2 generator, and you add all the highest spin generators, highest weight generators with arbitrary coefficients, so that will correspond to some charges for the background solution. So you can have, for example, a black hole with highest spin charges. So in this case, this matrix Q has this form, which you can, if you want to compute Wilson line between the points that are close to the boundary, then this will, so you compute it between the points, let's say, minus log epsilon 0 to minus log epsilon W. So W is just a complex variable that measures the distance between 2 points. So that this is the result. So it depends on epsilon, but you can do a nice trick. You can, if the points are close to the boundary, what happens that in this case, the Wilson line is dominated by just one matrix element of the matrix computed, for example, the one computed between two highest weight states. You can simplify it even further if you introduce, you can use the fact that, let's say, L minus operators, they annihilate lowest weight states, and L plus, they annihilate the highest weight states. You can introduce projectors on the highest weight state and the lowest weight state, and then you can find the trace of this matrix Q, so basically the Wilson line, in terms of the two quantities that do not depend on the holographic coordinates. So it's just something that is computed purely in terms of coordinates on the boundary of the cylinder. Well, you can do quite general calculation. You can, well, in some cases, you may be interested in representations that do not have lowest weight state. And for this, you can, in fact, all you need to do is to compute the, to do the calculation in the antisymmetric representations. And then for antisymmetric representation, so antisymmetric representations correspond to just one fundamental weight in the expansions for the highest weight. Then any highest weight can be obtained as the linear combination of the fundamental weights. Then the result for this matrix element, you can just you can write the expression for the Wilson lines in terms of just the product of the of this matrix elements for antisymmetric representations with appropriate powers. And in this case, you can analytically continue from, let's say, finite dimensional representations to infinite dimensional representations with non-integer constants decay. Well, again, so entanglement entropy is, you can get from this if you take the representation, the highest weight to be the Weil vector, so all these d equal to 1. It's a special case. In this case, even if you study the highest spin theory, you'll find that the highest spin charges in this case are all 0. So it's like a normal black hole. So just a bit of connection with integrability. Well, if you look at this matrix elements, so this is such kind of matrix elements are studied in the theory of tau functions. So tau functions are generating elements of generating functions for matrix elements of group elements of a group. So you can compute this in any representation for a given group G. So what one normally studies is the matrix elements or tau functions that are computed for group elements between highest weight and between two highest weight states. So you can use that and reproduce all other. So for any arbitrary element of G, you can introduce this time evolution given by the Bayesian operators, so which will generate. Well, in this case, that's actually t. This s, the t variables, the time variables. So you can this time evolution will generate all other matrix elements of this given group element G. And you can also, if you know, let's say, this tau function in one representation, in case of antisymmetric representation, you can also compute it in any antisymmetric representation using recursive relations that this matrix, that this tau function satisfy. Well, this study of correlation functions or Wilson lines and Chern-Simons theory in highest spin gravity theories, it suggests to look at some different kind of tau functions where you compute the matrix elements between highest and the lowest state. So they in principle related to the previously defined tau function, but there's well, because there's some number of derivatives involved, there's no guarantee that they will have this similarly nice properties. But they are, so there are two kind of tau for the connections that are studied by this higher spin theories. The tau functions do have these nice properties, and they also satisfy this Toda-like recursion relation. So somehow it happens that in this theory, what is nice mathematically is also nice physically. Well, that was not the main motivation of the study. So that this work that the project that I'm doing together with Andrei Mironov and Alexei Morozov and other people. So our primary motivation was to understand what's the importance of the knots in this picture. So this is something for a future talk, and I would like to finish here. Thank you. So